Yeah, I'm not going to be the one presenting, but I'm introducing. So, hi everyone, my name is John Perry. I'm a geological engineer with BGC, and I'm based in Madrid in Spain. I look after tens of thousands of kilometers of pipeline with respect to geohazards for various pipeline operators. In fact, BGC manages over 500,000 kilometers of pipeline. So that crosses over 150,000 watercourses. So we have a lot of data and a wealth of experience. So with that, I'm delighted to introduce two of BGC's hydrotechnical specialists. We've got Dr. Blanca, Marin, Esteve, and we've got Dr. Brett Eaton. Both hail from our Vancouver office. And they're going to talk to us today about their detailed assessments that we do at the most critical of our watercourse crossings. And they'll show how they've managed to translate research into pipeline integrity management and how they've streamlined our existing workflow. So as Lucas has put in the chat, if you do have any questions, please put them into the Q&A button, which is right at the top of your screen. We might not be able to go through them at the end of the presentation, but hopefully we can field those answers in the chat. So without any further delay, I'll pass on to Blanca and Brett.
Thank you. First of all, can everyone hear me and see the screens?
Yes.
I just need a thumbs up. Okay, perfect. So welcome. I'm Blanca, not Brett, obviously, and I'm going to be the one presenting the big picture of what tower tools are. So let's move on and see what exactly we are going to talk about tower and this Vortex-induced vibration. So the first thing is, let's talk about the concept. Let's see what we mean about this erosion. So the first video, don't look at the dancing pipe yet, just focus on the first video. It's what we think about erosion. So imagine you have a river and the river moves sediment, and sometimes it decides that he wants to dig a hole, and most of the times in places we don't want it to have a hole. In this case, you have an already existing exposed pipe, and the sediment transfer just like moving downstream and making the hole. So that's the erosion we are going to talk about. And then the dancing pipe. That's the video on your right. And in this case, we are showing what the Vortex-induced vibrations, the VAV for friends, are. So in this case, the pipe is already exposed. It has some erosion below. And then because these vortices, or like whirlpools, whenever you want to say, start to shake the pipe, and then you have this dancing queen. And at some point, if the shake is like big enough, you will maybe reach to fatigue. So none of them are good things, and those are the bad guys we are trying to avoid and that we are trying to predict. The next one is about why BGC. So if you don't know, we have like a large data set named Cambio. You can search on the internet what Cambio is. I suggest you do that before we continue with the R&D Symposium. You will hear that name a lot. So as John already said, we are here to talk about hydrotechnical crossings. So that's river crossings. So from all the lines that we have, we are just going to focus on the hydro one. And from all the hydro lines, we have a few, like you have the numbers there. I'm not going to try to say them, but from all the numbers, we're just going to focus on a few of them. So to know how we kind of classify from the big numbers to like the tiny detail assessment, that's the presentation that Aaron is going to provide, I think the last one of this session. So if you want to know how that works, I suggest you go to that one. So detailed assessment, that's like we know the pipe, or we suspect that the pipe is exposed or may be exposed, and that's when we do this detailed assessment, and that's when we run these tower tools. So this is a R&D, so we have a question to answer or a problem to try to solve. And the main reason we have this problem is because sediment transport is a phenomenon that it's been researched a lot, but there's still a lot of unknowns. So that's why we are here. And to add on the original problem, these exposures or like these scour, like the dancing pipes, happen most of the times with big events, so these massive floods. And I don't know you, I'm a hydro person, I love rivers, but I don't want to be nearby a river when it's speaking. Like, no, that's not safe. So taking real measurements when those events are happening, it's almost impossible. And then, like, come on, Blanca, we have flume experiments, we have lab experiments. Yes, I agree. And I've done a few of them, but the problem is that the experiments are not scalable, and sometimes they are just a simplified version of what's going on. And then, if you know about Manning equation and those things, like, come on, we have empirical methods, we have equations. It's like, I know, but the name, empirical methods, that's like data points that have a fitted curve to explain a phenomenon. The problem is that the data that you gather to obtain these empirical methods may not be applicable to the site that you're trying to predict. So even if like everything that I just said makes sense, the problem is about how we translate this kind of scour depths into exposure on a pipe, and how having a pipe in the middle of the river, it's going to change the dynamics. So with that, Reddit's going to explain like the details of like scour tools and why we are here today.
Great. Hopefully everyone can hear me. We're moving away from an approach to this kind of quantitative analysis where we might use spreadsheets to something that could be described as under the sort of rubric of reproducible science. This is a set of ideas that emerged in the late 80s, early 90s, when it became apparent that it's easy to go wrong when you're making lots of computations. And so you need a really structured approach. That's what BGC's leveraging, is this long history of improved workflows and a structure that focuses on decision points rather than individual calculations and making sure your spreadsheet's set up right. More fundamentally, though, when we do this right, this is how you mobilize research, mobilize field experience to do better management of stream bed scour. The fundamental building block for this, let's see, there we go, click. For this approach that we're taking is this thing that we call a reproducible computational notebook. And basically, if you know, you know. It's R Markdown, it's a Jupyter notebook, but the key point is that it's got two components. One is code. It is code that includes descriptive text, but as well as the code that loads data, processes data, makes figures. And then it also includes dynamic output. This is what the dynamic output looks like. It's a screenshot of an HTML document produced by some code that we use for Scour tools. You can see a number of different things in here. You can see at the top the headings and the descriptive text in black. That's where we set the context. That's where we describe what we've done in our analysis. And there's this gray box, and it's got some black text and blue numbers. Those are the parameters that we're defining. That gray box is what we call a code chunk. This is the actual, is a screenshot of the actual code that does the analysis. So that's the key idea behind this. We're generating records, we're recording the values we used, and in basically an instant we can rerun our analysis by changing a value and seeing what effect that might actually have. So what's the main reason? We sort of alluded to some of this, but there's lots of reasons why you might want to move from like a spreadsheet-based approach to RCNs, to this reproducible science model. You know, for example, it gives us better sort of decision-focused workflows where the analyst is focused on making the right judgments at the right points rather than making sure they understand how the spreadsheet works. It makes it possible for someone who is interested in and skilled at writing code to write functions that then can get checked and used by other people who are not necessarily code oriented. And it also produces that dynamic output. Every time you run the model, you produce output, a record of the analysis that has a date. So now it's got a date, it's got output that we can correlate to when it was run. We know exactly what the parameters were for the output that we get. But that's not the real reason. The real reason that we want to make this transition, the fundamental one, is there's some things you cannot do in a spreadsheet. They're limited. They're great for holding data. They're great for doing little bits of exploratory processing, but there are some things that they cannot do, and we're going to show you a great example of that in this presentation. There are 3 RCNs, reproducible computational notebooks, currently in our Scour tools system. The first 2 basically do what spreadsheets did up until earlier this year. They take input data, surveys, a flood frequency analysis, and other field measurements, and they apply them to a cross-section where there's a pipeline beneath a stream channel, and they get the hydraulics out of it. They figure out how deep, how fast, and how wide a stream channel would be for those reference flows. That is done in our first computational notebook, the output of which is then flowed into the second one, which is focused on guiding the analyst through selection of the right Scour model, evaluation of the parameters that you might put into that Scour model, and coming up with a set of Scour depth estimates. This is where the field judgment is absolutely key. This is where we really need a good focused workflow that gets us to values that we actually believe. But this isn't really new. It's just doing what the spreadsheets did reasonably well, and we're avoiding errors and uncertainties by structuring the workflow. This is something you cannot do in a spreadsheet. This is RCN number 3. This is where we take those predicted Scour depths and we turn them into Scour holes. Those Scour holes are then intersected with a pipeline to figure out how much of that pipeline might actually be exposed to the flow. So what you're looking at here is a Scour hole where the depth of the Scour hole is determined by RCN number 2, by our predicted Scour depths based on empirical equations. But that shape of the Scour hole is determined by a parameter that the analyst chooses. So is the location of the Scour hole. So we're leveraging both the experience of the analyst as well as some interesting new ways of generating and iterating geometry. We're actually moving the stream bed here to come up with easy to understand, easy to explain models of the Scour itself. So what does this do? We're producing these simulated Scour holes. They're not physically driven Scour holes, so it's a pseudo 2D kind of analysis that is used to predict our free spans. And fundamentally, that allows us to identify the flows that might produce a VIV failure in a pipe. We call those the flow of the concerns, and those that are likely to produce failure, which we call our critical flow. So that's just the tip of the iceberg. There's a lot more we can do with this RCN approach. There's a lot more that we're going to do with this RCN approach. And so this is just a taste of what's to come. Blanca.
So wait a second. Are you telling me it doesn't use AI, right? Like the whole world is going bananas with AI. And I guess everyone is going to look for AI. So, okay, to be honest, we did use AI for coding. So Brett didn't end like the frog in the GIF. And that's all. The main purpose of this kind of Scour tools is to make professional judgment the one who's making decisions. And right now, AI, it's not ready for that. We want the people to actually, the human being, making the decisions with like the knowledge, the expertise, the experience, and everything. However, the next steps, I think it's going to be with AI. So Scour are tools, and I hope you know now that this is not a typo, the capital R, it's because we coded in R. It's because we can add easily other tools. So one of them that's actually coming as a request from many clients, it's about reducing the uncertainty. So how we can do that? By asking AI, just like, hey, you're really good at looking patterns with data. We have those experiments on the video that have different shapes, like scour hole shapes. Just help us and find the trends. So that's going to reduce the uncertainty. We can also add multi-thread channels. So we have a side channel right now that's covered just like simplified to one. And the other one, I just to let you know that Lucy Mackenzie is going to present on session 2 today, bank region model, and that's also in R, so it's going to be easy for us to actually add it. And with that, that's the end of the first presentation. We are happy to answer any question that you may pose on the QA, and if not, you can contact Brett or myself on those emails. So, John, how are we on time?
Yeah, thanks, Blanca and Brett. We've got a minute or two, so there are a couple of questions in the Q&A. So let me just ask this first one from Wenja. The key parameter in the scour hole simulation appears to be the shape factor. Can that be related to properties of the stream channel, or is it constant for all types of stream?
Yeah, that's a great question, and we can put limits on it. We know that